In this second part of the video, I'd like to talk to you about power and how it relates to circuits. And the first thing I want to remind you of is that you already know about power and energy. We learned that previously. So these terms, energy or E, P or power, T or time, those should all be familiar how they're measured, what they mean. And what power means is it's how quickly energy is transferred. It's a rate of energy transferred, how much energy is transferred per second. And so I want to apply that to circuits. I want to think of this as my system, this light bulb with a battery, that's my system. And I want to think what happens at the beginning when I'm about to hook it up, and what happens after a few minutes when it's been hooked up for a while. So my beginning situation would be, oh, I'm just about to turn this thing on, and then my ending situation would be, oh, it's been on for a few minutes. And so my system is going to be everything that I see in there, the battery, the bulbs, maybe some wires. I know a lot of people like to throw earth in the system. That's up to you if you want to put earth in the system. But this is basically what I'm looking at, this circuit right here. And at the very beginning, before the light's turned on, really all we have in the circuit, we don't have really much motion. We are on planet Earth, so if you want to put Earth on there and say, oh yeah, it's got some height above planet Earth, you can, or you can call it height 0, but that's certainly not changing. We can put that at the end too. That's not the big thing that's changing. There's nothing moving, but the big thing is that there's a battery, and the battery stores energy chemically. It's stored in the chemicals in the battery. So I'd say, oh, there's a battery, it has some energy in it, and we're going to say that there's E-chem to begin with. And then after this thing's been on for a little while, the battery probably has less energy in it. So I know you think about plugging in a battery as recharging it, but it's not. It's really re-energizing it. And I say, oh, there's less E-chem. And I might ask, well, where did that E-chem go? Is there more motion? Maybe a little bit in the charges, but not anything significant. I don't see anything moving. Is it higher up in the world? Probably not. Probably what happened is the light bulb's been on, and so there's more E dissipated. That could be in the form of things like light from the light bulb, heat. Those light bulbs get hot. Resistors get hot. It could be in the form of sound if instead of a light bulb you plugged in a speaker or something. It could be in the form of motion if you plugged in a motor, but for the most part we're really looking at light and heat when it comes to light bulbs and resistors. So energy gets transferred, and we want to look at how fast energy gets transferred. That's a power situation. And so when I look at this thing, I think, well, how quickly is energy going to be transferred? How much light and heat am I going to get per second would be sort of a way of thinking about it. And so for me, I look at this and I think, well, how could I get more light every second? How could I get more heat every second? And when I look at the first bulb here and I look at the second bulb here and I think, well, this one's going to be much more powerful. If I was thinking in watts, like that's a brighter bulb, that's more watts, more joules per second here than here. So how did I accomplish more power? Well, it looks like I have a bigger pressure difference across this bulb, a bigger voltage difference, delta V, and I have a bigger current through this bulb. So it looks like both of those things matter. The equation that makes most sense to me for power is that power is I delta V. And what that means is more current makes a brighter bulb, makes a more powerful situation. And more pressure difference also makes more power, makes energy be transferred quicker. So this is the equation for power, but to be honest, there are other versions that work just as well, and we can derive those. First of all, you'll see up here, I is delta V over R, that's Ohm's law. So I could derive another one by saying, oh, instead of I times delta V, I'll just sub in. Oh, I know what I is. It's delta V over R. And then I keep that delta V here. So version number 2 is that it's delta V squared over R. And that's just as good as the first one. It just depends what you have. If you have delta V and R, you'll want to use this one. If you have I and delta V, you'll want to use that one. There's another version I could do too, because if I is delta V over R, I could also write delta V as I times R, and I can sub that into my original power equation too. I'll substitute for delta V, I'll substitute I times R, and then I get my third version, which is I squared times R. Those are all good for circuits, but then there's the general equation, which is still totally fine. It's this one, power is how quickly energy is changed. I guess I should write change in energy over time. Change in energy over time. So any of these four are good for power. This one makes most sense to me because the more current and the more delta V, the brighter my bulb is going to be, the faster it's going to change energy into forms like light and heat.